On May 1st, 2005, Cassini's narrow-angle camera looked into a dark cut near the outer edge of Saturn's A ring. In a gap only 42 kilometers wide, it picked out a moon about 8 kilometers across. The moon is Daphnis. Its gravity was small, but the ring answered visibly. The gap edges bent into waves, and later images showed icy ridges lifted far above the flat ring plane. That was one strange object inside a much stranger disk. Saturn's main rings stretch almost 280,000 kilometers from side to side, yet in many places they are only tens of meters thick. They contain the wide Cassini Division, the narrow Encke gap, embedded moons such as Pan and Daphnis, and lanes that look empty even where no moon is sitting inside them. Cassini's prime mission was less than a year old. The close study of the rings had only begun. Saturn's gaps are not tiers in a solid sheet. The evidence points to two main sculptors, small moons that clear material nearby, and orbital resonances that pull particles out of place from far away. What remains open is how collisions, ring thickness, and small unseen bodies keep some edges so sharp. The first step is to stop picturing the rings as a single surface. They are a crowd of icy particles, from dust grains to boulders, each moving around Saturn on its own orbit. The bright sheet is the combined light from countless separate pieces. That matters because a gap is not a crack. It is a region where fewer particles survive on stable paths, or where particles have been pushed into neighboring paths. Even the darkest divisions are not perfectly empty. Spacecraft images and occultations show material inside many of them. An occultation is a simple measurement. A star or radio signal passes behind the rings, and the rings block part of the light or signal. The amount blocked reveals how much material lies along that line. These measurements show that Saturn's rings are structured on scales from thousands of kilometers down to tens of meters. Once the rings are understood as orbiting particles, distant moons can make gaps without entering them. The key word is resonance. A resonance is a repeating gravitational tug. It happens where a ring particle and a moon return to the same relative position again and again. A single weak pull does little. A repeated pull at the same point in the orbit can build up. It can make a particle's path more oval. In a dense ring, that disturbed particle collides with neighbors. Over many orbits, material is spread away from the resonant location. This is why some gaps look as if something invisible has cut them. The cutter is not hidden in the lane. It is a moon elsewhere, pulling on a schedule set by orbital arithmetic. The Cassini Division is the most famous dark band in the ring system. It lies between the bright B ring and the A ring, and it is about 4,800 kilometers wide. It is not empty, but it is much less dense than the bright rings beside it. Near its inner region, ring particles orbit Saturn twice for every one orbit of the moon, Mimas. That 2-to-1 resonance is strong enough to disturb particle paths. The best explanation is that Mimas helps maintain part of the division by pumping energy into those orbits and letting collisions remove material from the most affected zone. This does not mean Mimas alone explains every detail. The Cassini division contains ringlets, smaller gaps, and changing edges. Other resonances and the ring's own collisions also matter. The broad darkness is an established feature. The exact history of how it formed and evolved is more complicated. Some gaps have a more direct cause. The Encke gap sits in the outer A ring and is about 325 kilometers wide. Inside it orbits Pan, a small moon roughly 30 kilometers across. Pan does not sweep the gap clean like a snowplow. Its gravity scatters nearby ring particles and prevents many from remaining close to its path. The Keeler gap is narrower, about 42 kilometers wide, and Daphnis orbits inside it. Daphnis is only about 8 kilometers across, but its inclined orbit makes the ring edge rise and fall. Near Saturn's equinox, when sunlight skimmed across the rings, Cassini images showed long shadows from vertical structures at the gap edge. These moons prove that very small bodies can shape enormous-looking features. A moon far smaller than a city can hold open a lane many times its own width. The sharp edges are not static walls. They are moving patterns in a disk of colliding ice. A moon can launch spiral waves, scalloped edges, and wakes that wrap around Saturn. The pattern may look fixed in a photograph, but the particles pass through it. Prometheus, a moon just inside the F ring, repeatedly pulls streamers out of that narrow ring. The result is a changing chain of channels and clumps. This same principle appears throughout the ring system. Gravity creates a pattern, collisions soften it, and new tugs rebuild it. That balance explains why many gaps are only partly empty. Gravity moves material away from certain orbits, but collisions and spreading push material back. A gap is maintained only where the clearing process wins often enough. Cassini also revealed propellers, small disturbances shaped like paired blades in the A-ring. The supported interpretation is that they are made by moonlets too small to open a full gap. They disturb nearby particles, but their gravity is not strong enough to clear a continuous lane around Saturn. These features show the limit of the simple answer. Large moons and strong resonances explain the main named gaps. Embedded moons explain several narrow lanes. But the fine structure depends on particle size, collision rates, self-gravity, and the number of moonlets hidden below direct detection. Those details are still uncertain. Better answers would require measurements that resolve smaller particles and track the same structures for longer spans of time. Saturn's strange gaps are the visible result of gravity acting on a thin disk of separate icy particles. Some are carved by moons inside the rings, such as Pan in the Encke gap and Daphnis in the Keeler gap. Others are maintained by resonances, where a distant moon pulls ring particles on a repeating schedule. The answer is settled at that level. The gaps are not cracks, and they do not require missing matter to be hidden somewhere else. They are places where orbital paths have been made unstable or less crowded. What remains open is the fine print. The sharpness of some edges, the lifetime of some narrow features, and the population of unseen moonlets are still constrained rather than fully known. The broad sculptors have been identified. The exact grain-by-grain maintenance of Saturn's rings is the part still being measured. That's why source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.